Good evening, everyone. Hope you're doing well. And let's go ahead and start a discussion about geological resources. And I'm going to let you know in advance that this lecture is going to be a fairly long one, and it's going to cover a lot of material relatively quickly. And that's basically because of where we live in California, which is a geologically very diverse state. There's a whole lot going on here. And so there's a lot of potential topics to talk about. Generally, because of where we live, there are things like the wonderful geological formations, the rock formations in places like Joshua Tree National Park, and of course, California's complex geologic and tectonic history is also responsible for there being places like Yosemite. So there are all sorts of things about California's geology that we enjoy, that we are that excite us and fascinate us. But there's also a lot of resources in terms of being used by people to create wealth or provide satisfaction. And those are the main things we're going to focus on today, particularly things like petroleum, but not exclusively petroleum. And to get to that point, and I'm going to focus a little bit on California, but we're also going to look at things more broadly. So if we look at how humans consume resources through time, you can see over here that wood was a major source of energy for a variety of years. And this says, going back to the year 1775, clearly humans were using wood as an energy source long, long, long before that. And the energy in wood derives specifically from energy that was stored in the organism's cells when it was alive. We've already talked about that, how plants will take in solar energy and they will store some of that energy. They will use a small proportion of that energy. When that plant dies, the energy that was still in its cells stays there. And unless the plant falls apart completely, that energy remains in those plant cells. So when you're looking at wood, whether it is modern or earlier, and when you burn wood, what you were doing is releasing the energy that that plant, when alive, had absorbed from the sun, and you're releasing that energy. And as humans became more industrial, as our societies grew and as they spread, that source of energy became more and more useful. This is actually a photo of a wood powered train. So they were using wood as fuel to drive this locomotive. And that should give you an idea of the energy that is available to us in from wood. And you know this from throwing logs on your fireplace, whether you're or, on your fire, whether it's in a fireplace or camping or what have you. If you've ever burned wood before, you're aware that it gives quite a bit of heat. But also needs to be renewed. It needs to be replenished. If you're out in the desert with a campfire, you're going to need to keep putting wood on it until you're done for the evening, because it does have energy in it that can be released by burning, but also a limited amount. Eventually, as society grew and became more industrial, there was a switch over to coal. And here's a map showing where we have major coal deposits. Here I'm focusing mainly in the United States. You see, there's not a lot over there in California, but there's a whole bunch back east. It's very thick with coal deposits back east that go on for mile after mile after mile, which is how in the early days of the nation, that's how coal became such a driving force. And it wasn't just in the United States, it was also in Europe, England, and so forth. The reason that this is here, though, well, before we get to that, sorry, coal is a source of energy much better than wood because it's actually compressed plant matter. As of about 2016, there are an estimated 1.11 trillion tons of proved recoverable oil available in the world. Each U.S. ton of coal is capable of producing, on average, just under 19 million British thermal units or BTUs of heat energy. I am not sure if I'm going to test you on that number or not. Think around 18 million, 19 million. Try to keep that in mind, but we're going to talk about it later this lecture. And so I'm not sure if I want to get this specific on an exam, or if I want to be a little more general. I'm still working that out. But the energy that is being released, those British thermal units of energy being released, were stored in those deposits back when the organism was alive, when it was absorbing solar radiation and storing some of that to use as materials. So this lecture actually, even though it's about geological resources, it's covering the biology angle from a couple of different ways. Number one is the energy we use, and number two is where the energy came from. And again, specifically, the energy is coming from ancient ecosystems. Now, this is a artist's representation, a scientific artist's representation of what North America would have looked like about 345 million years ago. And if you're looking closely, you can see the United States and the Canadian territories mapped onto this diagram. And this is based on the available rocks that are at the surface today, where they occur, and what their age is. And what I want you to do is look over there on what today would be the east coast of North America, right in that region. And note that even at this point in time, 345 million years ago, it's dry land. And at this point in the Earth's history, it would have had major forests on it. And day after day, week after week, month after month, year after year, for millennia, for even longer, those plants would live and die, and the ones that were living were taking in energy from the sun, and the ones that were dying were trapping that energy in their body tissues, and it stayed there as those plants got buried. So, this is 345 million years ago. This is 20 million years later. And 20 million, when I phrase it like this, it might not seem like a long time. But 20 million, if you go back from today, go back 20 million years ago, pretty much none of the animals you're used to seeing are around. There's no hominins to speak of. Camels and horses and so on are going to be extraordinarily uh, different from the ones we see today. Um, and so it's a huge span of time. And yet, from 345 million to 325 million years ago, this area remained mostly dry land. And those forests kept living and kept dying. And as they died and got buried, they kept storing the energy that was trapped in their tissues. This is another 10 million years later, and you see that it is still dry land. It still had forests on it. This is still living, dying, storing energy. This is 300 million years ago. So we just covered almost the same span of time as between us and the extinction of the non avian dinosaurs, just in these maps. And through that whole period, this area has remained dry land with major forests living and dying and doing their normal biological thing. And as those deposits of wood build up and build up and build up and build up, they store incredible reserves of oxygen, or excuse me, of energy. And that today is where we find all of these coal deposits. That's where those coal deposits came from, is from those ancient forests deposited over tens of millions of years. And it's where the energy in those coal deposits comes from. It's from those ancient ecosystems. You can also see here, as I showed you in the earlier map, there are some other coal deposits, not nearly as extensive, but you've got some in Colorado and Utah and Wyoming and up into Montana. And if we get rid of that map, you can see that there are chunks of the continent here as well that were dry land and would have been forested to some extent. So not nearly the extensive coal deposits of back east, but still quite a bit of coal available from these areas. This is where California would be, and you can see there's almost no dry land here at all, so you wouldn't expect to find a lot of coal deposits in California, and you would be correct. But there have been coal mines in California. This is the Black Diamond Mine outside of Nortonville back in about 1880 that was actually mining coal right here in California. So it did happen, but it wasn't nearly as extensive as what we see back east. Once again, what we are looking at is capturing the energy of ancient ecosystems and burying it and preserving it. And then once these organisms have all died and been deposited and been covered, then it's just a matter of time and heat and pressure. all of them working together to convert all those plant layers into a peat deposit, and then subsequently from peat moving into a lignite or brown coal, and then eventually becoming the sort of coal that is being mined today in order to generate energy for our use. So it's a geological resource because it's preserved in the rock record, but it is also a biological resource because it derives from ancient organisms. Just as an aside, I probably won't test you on this, but this is actually a picture of a peat horizon that's about 41, 42,000 years old. And this was found during excavation of Diamond Valley Lake down in Hemet. And so this shows that here in California, you can have the formation of peat. Back at that time, 41, 42,000 years ago, you had a lot of plants. They died, they were buried, they were compressed, they were subjected to pressure and heat, and eventually they became this peat horizon. Now, this peat horizon was exposed during excavation, and we documented it when we found it, but now all of that is buried underneath present-day Diamond Valley Lake. So it was 40 feet below what is now the floor, or what was the original floor of the valleys, and now it is below all of this water. But probably this whole area during the ice ages would have had plants living, dying, being deposited, and getting to that first stage of peat. And then if you had waited another several million years and continued to apply heat and pressure, you might even have had coal deposits here as well. But I'm not planning on being here in another 10, 20, 30 million years, so I'm not going to find out about it. Now, once again, point to take home is that the energy preserved in these ecosystems, that is everything we have been talking about, the entire period about how energy moves through systems, is what is released when we use coal as a source of fuel, as a source of energy. That's the energy being released. It's from ancient ecosystems. And so coal mining had so much energy in it that despite the dangers then and now, it was hazardous. And actually, these are people working here. They even had horses that worked down in the mines. And apparently, from what I've read, I wasn't there, um, never saw the light of day. They spent their entire lives below the ground helping to move coal back and forth, which to me sounds horrific. But the coal that we're talking about is what really drove the Industrial Revolution and provided the energy necessary for expanding the railroad, for expanding uh, uh, industry, and so forth. Today, coal is not used so much for things like transportation. It's used mainly for working with hydroelectric and so on and generating power rather than generating motion. But we still use coal today. The reason we don't use coal as much for things like transportation is because of a shift over to petroleum. And petroleum is the same sort of thing. Once again, it is derived from ancient ecosystems, and the energy that was trapped in those living things when they died remains available for our use. This is actually a shot from out in Kern County, California. And it gives you an idea, if you've never been there, it gives you an idea of the extent of some of these oil fields and the petroleum that's being extracted right here in California. So if you want to drive up to Kern County and take a look around, places like Maricopa, places like McKittrick, places like Taft, you can smell the oil in the air, and you can certainly see the evidence of the petroleum being harvested. But it's not just in Kern County. If you go back far enough, Los Angeles and other parts of Southern California had extensive oil deposits. This is a shot from 1894 in Los Angeles. This is the Long Beach area back in 1937. Yes, those are all oil derricks, and it shows the extent of oil deposits in this area. This is Long Beach in 1948. I like the fact that they were even selling Tecate beer back then. In fact, it makes me want to have one, but I'm going to wait until after the lecture. But this is what it looked like back then in Long Beach. And for those of you who visited Venice Beach, this is what it looked like as recently as 1952. So there's oil all over Southern California. Now, in terms of global oil, as of 2016, the same year as what I gave you for coal, There are an estimated 1.65 trillion barrels of proven crude oil reserves in the world. I'm going to come back to that point. Probably not this lecture, but in a future lecture, I'm going to come back to what constitutes proven crude oil reserves, because I think that's important for you to know. But I'm throwing so much information at you this lecture that I'm going to wait till a future lecture to talk about that sort of thing. In any event, 1.65 trillion barrels of proven crude oil reserves in the world. Each barrel of crude oil is capable of producing 5.5 million or so British thermal units of heat energy. Now, petroleum is generally liquid. So converting the energy obtained from oil to compare it with the energy obtained from coal means you need to do a little bit of math. And fortunately for you, I have done the math. There are approximately 6.84 barrels in a U.S. ton. I am not going to test you on that, which means that a U.S. ton of crude oil would produce almost 38 million BTUs of heat energy, compared to only about 19 million per ton of coal. So oil is almost twice as energy rich as coal is. And that's one of the reasons it became such a useful commodity, so important in supporting our current way of life. It's because there is so much energy. And again, that energy comes from ancient ecosystems. It also comes with some peril because oil is liquid. It can get out of control. This is actually an aerial view of an oil spill along a California beach from a few years ago to let you know that yes, sometimes oil can get away and it can really wreak havoc. And it's not doing that as a consequence of being oil, it's doing that as a consequence of humans using it as a resource, as a commodity, and it getting out of control and away from people's control of it. Now, what happened was petroleum pretty much overtook coal right here, and you'll see that's about 1945. This is at the end of World War II, which we're going to talk about again. We talk about World War II a lot, almost as much as we talk about the Roman Empire. But what you're looking at is in World War II, in Germany, particularly in Italy, they still relied primarily on coal-powered vehicles, whereas the Allied powers, particularly the United States, after they entered the war, were depending on petroleum-powered vehicles, which, as we just discussed, would have had more energy for less weight than coal-powered vehicles. So that was part of the advantage that the Allies enjoyed during World War II. And after the war, petroleum continued to take off as a primary energy source. And as we discussed, coal was relatively diminished in terms of things like um, transportation and so on. Oil is still being consumed today, and not just up in Kern County. These are oil derricks down in Orange County, California, which you can drive down and see today. And they're pretty clearly oil derricks, so we're still producing oil in California. Some oil derricks are less obvious. This isn't there anymore, but this was an oil derrick, which was covered by that decorative framework right next to Beverly Hills High School. So right there in the heart of Beverly Hills, you had an active oil derrick until just a few years ago. So again, even in LA, there are still buildings like this, which may not look terribly impressive to you and I driving past them, but inside it would be an oil rig. And the whole point of building this contraption around it is so that you don't necessarily see it and think about it. You're not aware that it's there. Where does the energy come from? Well, if you're as old as I am, you probably remember commercials from, I believe it was Chevron, where they talked about how ancient dinosaurs were when they died, they eventually turned into oil, and so that's what you were using when you were driving. And there's a dinosaur in your gas tank. And if you aren't as old as I am, you might still be familiar with memes like this one, where if plastic is made out of petroleum and petroleum is made out of fossils and fossils are dinosaurs, then plastic dinosaurs are real dinosaurs. And it's amusing, and maybe you're laughing at it even as we speak, but it's also inaccurate because dinosaurs are not involved at all. The organisms that are involved in producing oil are marine organisms. And what happened is they died on the ocean floor and then were buried by subsequent deposits of sediments. And then, just as we saw with coal deposits, they were subjected to heat and pressure and eventually turned into oil as we understand it today. So, this is a diagram showing how petroleum and natural gas, which we're going to talk about in a minute, this is how all of that formed. Tiny sea plants and animals dying, being buried, and being squeezed into porous sedimentary rock and eventually filling the pores in that sedimentary rock to become oil. And so that's what we drill down to today, where these rocks are exposed or where they're buried to get the oil out of them. And as you can tell from this map, oil deposits are much more extensively distributed than coal deposits were. We've got oil all over the place, including, as we've just discussed, plenty of oil deposits right here in California, in Southern California and Central California. And so this is what you see going on out in Kern County today, is actively harvesting all of that oil to the best of our ability. You can even go there and see oil seeping out of the rocks. This is my colleague, a paleontologist named Kristen Brown, and she and I were surveying out in that area, and you can hopefully see that the dirt she is touching and the dirt all around here is saturated with petroleum. Now, it's not so rich that you would sink a well here and try to extract it. Nevertheless, it is, again, if you go to this area, in addition to the oil rigs that you'll see actively working, you will also see some of the sediments actively have, uh, in this case, probably asphalt or something similar leaking out of it. If you would rather not go inland to Kern County because it's so hot and it's so dry and it smells like oil, you can go to the coast in Carpinteria where there is a tar pit beach. And here you can see the same thing. This is right along the beach. The Pacific Ocean is behind me as I take this picture. And you can see asphalt leaking out of the rocks there because it was preserved in these rocks and continues to leak out and bleed onto the shore there. Um, so if you're in California, there is still a lot of petroleum not only being harvested, but also simply being exposed in nature. If you don't want to drive to Kern County and you don't want to drive up to Carpinteria and spend some time at the beach, you can still see this sort of thing if you drive into Los Angeles and go to the La Brea tar pits, where you have active asphalt seeping to the surface. And asphalt is a petroleum byproduct. It's oil leaking to the surface, and then the lighter elements evaporate, and you're left with sticky asphalt. And so that's what you see going on at the tar pits today. And that's why we have all of these organisms living, or excuse me, not living anymore, preserved at the La Brea tar pits today. It's because back during the ice ages, these tar sips were also active in the area. And as a consequence, these animals would get stuck in the sticky asphalt and get trapped and eventually get buried, and their bones are preserved so that we find them today. And because of the nature of the asphalt that they're preserved in, the bones are actually 100% real bones. The mineralization that takes place for many fossils hasn't taken place at the La Brea tar pits, and the asphalt saturates the bone and preserves it completely. As I've already mentioned, I used to work at the La Brea tar pits. This is me working back there in 1989. I'm holding a saber-toothed cat hip bone that we had just excavated. And the reason I bring this up is not to brag about those years I spent at the tar pits, but to emphasize that one of the things that happens even today is that organisms get stuck. Even today, you can see pigeons and so on getting stuck at the tar pits. And so the question is also often asked, what about people? Do any people get stuck in the tar pits? And the answer is only the stupid ones, which I will count myself. This is an article from 1989 where I told the New York Times is a story about me getting stuck in a tar pit. I thought we were off the record, and we were not. So I went to school the next day. This is when I was at UCLA, went to school the next day, and all my fellow students were pointing at me and laughing because they read this in the New York Times, and I wasn't aware I had got my own sidebar about the day I got stuck in the tar pits. So keep that in mind next time you're interviewed by anybody from the newspaper. Nothing is off the record unless they specifically state it in advance. Anyway, that's an aside. I might test you on that just for fun, but I probably won't. Because petroleum comes in liquid form, And because it has so much energy available, it's easier to use than coal is. And so that's why the automobile industry really took off with the advent of petroleum. Yes, as I just mentioned earlier, during World War II, there were coal powered vehicles as well. And for a while, there was competition about which energy source would be better. But because you needed less weight of petroleum to generate the same amount of energy, you're able to more efficiently design vehicles like this. And it wasn't so much in the automotive industry that this really kicked in, but in the aviation industry. If you think about trying to fly some of these early planes and trying to do it using coal, it would have been impossible. You wouldn't have been able to shovel the coal. You would have needed too much coal. You would have had too much weight and not enough energy released by that weight. So the fact that we fly today is enabled by our consumption of petroleum as a resource. So those ancient ocean floor dwelling organisms that lived and died completely oblivious are the reason that we can fly from continent to continent today. It's also why we can fly to different celestial objects today. The Apollo program was powered by petroleum products. In fact, the whole first stage, the one that you see working right here, the bottom stage, was powered by kerosene, which is derived from petroleum. The energy of ancient ecosystems was released in a staggering manner. The Saturn V engines were incredibly powerful. And that's how we got to the moon back in the 60s and the 70s, was releasing the energy of ancient ecosystems. Beyond energy, petroleum gives us a variety of other products. Most plastics today are petroleum based, and it is true that some people are trying to develop other plastics that are plant based, and that is a worthy effort moving forward. But by and large, the vast number of plastics that you use in your life are derived um, from petroleum. And if you think about where you are right now and what you're looking at, are you looking at a laptop? Are you looking at a phone? Think about the amount of plastic in those, and that's almost certainly derived from petroleum. So it's all around you. It's our entire way of life, literally, no exaggeration, is based on petroleum. There's no way around that. It is the single most important element in civilization as we understand it today. Beyond plastics and beyond energy, we also use oil as a lubricant so that we can keep our gasoline powered vehicles driving smoothly and effortlessly. And we use that oil again to pave the roads that we're driving on. And so there's any number of uses for petroleum. It really is integral to pretty much every aspect of our way of life, um, which is an important point, and I'm going to come back to that in a future lecture. Now, in addition to petroleum, in those same deposits, as I mentioned earlier, there is also natural gas, which is laid down as part of the same ancient marine ecosystems. But, and this is an important point, and I will probably test you on this, you can also get natural gas from terrestrial ecosystems as well. And that's why, here's something to remember for the exam, you have more extensive deposits of natural gas than you do either petroleum or coal, because you have natural gas forming from both terrestrial and marine deposits of ancient organisms. So keep that in mind. If I ask you which is the most widely distributed resource, be aware of what it is and be aware of why that is. Now, natural gas we use for any number of things. It does provide a fair wallop. Uh, Again, because it's a gas, we're going to have to change things up a little bit to compare it to petroleum and compare it to coal. So, as of 2020, there are 7,257 trillion cubic feet of proven natural gas reserves in the world. Each cubic foot of natural gas is capable of producing a little over 1,000 British thermal units of heat energy. Now, as I just said, comparing BTUs of natural gas with those of oil or coal is a bit of a challenge because you're talking about a gas versus a liquid versus a solid. But if we use a metric known as the barrel of oil equivalent, and we make some assumptions, and I'm not going to dive into the math here, number one, because I'm bad at math, and number two, because I'm not expecting you to know the math. Um, roughly 6,000 cubic feet or so of natural gas would produce the same energy as a single barrel of oil. And based on that, natural gas has less energy density than oil, but more than coal. So it's a little bit different. And because of the energy availability of natural gas, we use it for any number of different things, even in the house. Fireplaces, water heaters, barbecue grills, gas dryers, heated pools, and so on. The challenge with natural gas, though, is that it needs to be under pressure. It needs to be in a container that keeps it confined and pressurized. It's not like oil that you can just pour in a plastic tank and move it around that way. With gas, you actually need to keep it under pressure. That's why your propane tanks are pressurized and you release them with a valve and so on. So that's one of the considerations when using natural gas. Now, all of these are natural resources derived from biological systems but preserved as geological resources in the rock record. And we use them as resources, which brings us back to the concept of carrying capacity. Once again, the size of a population that can be supported indefinitely based upon the available resources and services of the ecosystem. And in this case, we're looking at food, water, and space. And so you're thinking, well, are we eating the coal? Are we eating the oil? I really hope not. Please, if you think I'm suggesting that these could be a food source, no. But they can certainly help us recover food. And in fact, the way agriculture is conducted today depends hugely upon the availability of fossil fuels, mainly petroleum, but also including natural gas, to help the harvest, to keep providing food for the 8 billion plus people that are on the planet today. We've already talked about how the grain that's being harvested in the United States is going towards cattle. That grain going towards cattle supports the beef industry, which means next time you are having a slab of beef, this is actually from a place called Spirit of Texas Barbecue up in San Bernardino. If you were so inclined, it's pretty yummy, but it's very pricey these days. This is an older picture. Nevertheless, this beef was produced in part by using fossil fuels, not just to provide grain for the cattle, but also to transport things. Again, petroleum is interwoven into pretty much every aspect of your life. If you're eating something, chances are excellent that unless you grew it in your own yard, petroleum was involved in the processing and the production of whatever it is you're eating. Petroleum also enables us, coal too, let's say fossil fuels also enable us to move into areas and provide heat where otherwise we would find it very difficult to survive in large numbers. So you have communities. This is actually up in the Yukon region of Canada, and you can see those. It's cold. It was cold. This is in February a few years back, and it was very, very cold. But you can also see quite a few people living there. And this was taken outside a nice little restaurant where we had some beer and some other stuff because it's a community, and so you have restaurants and you have gas stations and so on, even in these areas, and that is enabled by being able to produce heat from fossil fuels. And getting to these areas is also enabled by petroleum. When we fly today, if you've ever flown anywhere on a jet or even on a prop plane, you've used petroleum byproducts in order to get there. So, once again, keep emphasizing our entire way of life is based on the availability of petroleum and other fossil fuels as a resource for using the energy that was trapped in those resources from ancient ecosystems. Next time you're driving, next time you're flying, think about every time you accelerate, you are burning energy that came from ancient ecosystems. Keep that in mind. Now, we talk about these ancient biological processes. Remember that whether it's marine or whether it's terrestrial, we're still looking at this. And in most cases, with coal, you're looking at the producer level where you have the maximal amount of energy stored. If you're looking at things like marine organisms, in most cases, they are going to be at least primary consumers eating plants. And in those cases, you have relatively limited energy. So it's not the energy just in the ecosystem, it's the volume of material and the amount of time needed to take that and produce it and store it for our use today. In order to release that energy, there are other byproducts. There are, for example, emissions that get into the atmosphere, greenhouse gases. We're going to talk about that, I think, next lecture. So I won't get into it here, but be aware that it's not just necessarily a clean conversion into energy. There are byproducts, and those byproducts can be hazardous as well. So we'll talk about that next lecture. There's also byproducts like this, which we've already mentioned. There's the pollution that comes from increasingly using plastics and generating plastics. And so this is something we have a very plastic focused society. And so as these plastics continue to survive, they break down into smaller bits, but then they don't go away. We continue to pollute the planet with the byproduct of our consumption of petroleum products. Now, are there other sources in the earth that we can use for energy? And the answer is absolutely yeah. Yes. For example, there's geothermal energy. This is actually from up in Yellowstone. This is one of the springs up in Yellowstone from a few years back. And essentially, what you do with geothermal energy is tap into subterranean water that is heated or inject water into it in order to, keep things cool, depending on what time of year. And the heat from that water can then drive turbines that then can produce energy and so forth. So it's taking advantage of natural features available in the rock record without consuming them, without burning them, but still finding ways to convert that into energy that we can use, basically by driving steam turbines that then produce energy that we can use. So during the summer, for example, you can pump water, you can pump water, hot water down into these reservoirs, and it stores the heat there to keep things cool during the summer. And then you can reverse that process and bring heat up from that water during the winter to warm things up. So there's every possibility of using this. And again, you're using a resource that is available without necessarily consuming it. You're cycling it, but you aren't consuming it, you aren't burning it the way you do with fossil fuels. So this would be a geothermal heat pump. One of the cool things about geothermal energy is that it's available in any number of places around the world, including places like the Arctic and the Antarctic, where you have, if the conditions are right, you can take advantage of subterranean heat, even when you have icy conditions at the surface. In the continental United States, exclusive of Hawaii and Alaska, you have a variety of geothermal resources available. In this diagram, you can see that the darker red the part of the map, the more geothermal resources you have available. And hopefully you'll notice that down there in Southern California, south of us, we have geothermal capabilities there as well. And this would be in the area that you probably have visited, known as the Salton Sea. And what's happening with the Salton Sea and the area around it, this is what it looks like from space. And if you go back and take a look, this is where the San Andreas Fault is. Okay, we've talked about the San Andreas Fault before, but in these areas here, you go away from being more of a slip slide sort of thing, like the lateral faults that we talk about with San Andreas. And here you've got kind of a pull apart basin, which enables geothermal energy to be happening. There's Los Angeles up in the upper left. And this has been taken advantage of. There are right now geothermal energy facilities down in that part south of the Salton Sea that are actively producing energy. So the awareness of this area for that sort of energy being produced is known and is likely to expand should the Salton Sea continue to get smaller through time. But that's a different lecture. Now, the other things that are preserved in our rock record are basically not derived from ancient ecosystems, but they are derived from the way the planet itself formed when the solar system came to be. And you can see an example of this next time you drive out to Las Vegas. For those of you who have been to Las Vegas, you see it up there at the top of the screen. This is a Google Maps image, and the area we're looking at is right down there. So next time you're heading out on the 15 and you get up into the Mountain Pass area, right before you come out of Mountain Pass and you hang a hard left and you head down into the Prim area and then off to Las Vegas. As you're driving through the Mountain Pass area, take a look north of the freeway and you'll see a mine known as Molycorp Mine. And this is where they are mining for rare earth materials, and they have been for quite some time. This is what it looked like back in 2006, again using the go back in time feature on Google Earth. And so you can see the central pit there and some of the side pits. And the reason I picked 2006 is not because it's a year that holds any particular special meanings for me, but because I was working as a curator at the San Bernardino County Museum at the time. And we went out and visited this site and got a behind the scenes tour. And it was very easy. We pretty much showed up and they said, "Yeah, let's take you around." It was a lot of fun. We took notes, we took pictures. And what struck me is how much work wasn't going on then. It just didn't seem terribly busy because the rare earth materials being excavated weren't necessarily as valuable as they are now. Here's some of the material that's being produced, and you can see the list there. This is one of the displays they had in their main office, and you've got minerals that are being mined for use in television and computers and lighting and telecommunications and so on. All right, so we had a nice behind the scenes tour. This is what it looked like in 2006. This is what it looks like today. It's really, really, really expanded because those rare earth materials have become so much more valuable. And this area is one of the few areas in North America where you can effectively harvest these materials because they're relatively close to the surface. And so this excavation is still going on today. But now, if you drive to Vegas and you look north of the 15 freeway and you see them, you will probably see parking lots full of cars and you will see lights and you will see steam and you will see it going 24/7 throughout the year because those minerals being excavated are so valuable and so needed for the way we do things today that it's essential that the work continues. So even though we don't see oil necessarily as expansive as it used to be, and coal has pretty much fallen by the wayside, nevertheless, you head out to Vegas and you can see this north of the freeway, and you can see that this is actually another source of energy. And so the excavations are still going on out there today. All sorts of different elements. Now, this is what we use rare earths for. And you can see that 62% of it helps with petroleum refining, it helps with catalytic converters, it helps with chemical processing. You can see it's also used for computers and hybrid vehicles and so on. I'm not going to test you on these percentages, but be aware that this is what we use these minerals for. And the reason I'm emphasizing this is because they are present in finite amounts, because they were captured when the Earth formed. You had essentially a solar explosion, and that explosion smashed atoms together. The universe is full of hydrogen. And when you have supernovae going off like this, the pressure from that can smash those atoms together with unbelievable pressure that we still haven't even managed today to produce as humans. But it happened billions of years ago. And then as these materials settle and gravity starts to weigh in, as you have concentrations of some of this material and you start to have the ignition of a new star, and then you have these materials forming around that new star, all of the planets and asteroids and so on that are forming are incorporating some of those rare earths that were formed by that initial supernova, by that smashing energy from that detonating star. And so once the earth forms, all of the rare earth minerals that were trapped in the earth as it formed are all we're ever going to get. That's what's out there. That's it. So as we use those minerals, we are using a very limited supply. Granted, the earth is quite large and there are a lot of those minerals, but there's a reason they're called rare earth minerals. It's because they aren't as abundant as other minerals that you might be able to think of. Uh, Minerals like uranium or elements like uranium are relatively rare on the planet, and we use this as an energy source. And now I'm going to talk a little bit about how uranium mainly was first used. This is the advent of nuclear power, and nuclear power really got its start in World War II, where scientists were studying how to use radioactive materials like uranium to make bombs. And that's what happened at Hiroshima when an atomic bomb was powered by uranium was detonated. And essentially, what happens, I'm not going to test you on this, but I just want you to be aware that what we're talking about here is nuclear fission. And some of you may know about this, but essentially, what you're doing is using a conventional explosive over there on the left to force a hollow uranium bullet into a target. And what that conventional explosion in this contained feature is essentially duplicating what happened with those ancient stars that detonated. But in this case, instead of smashing atoms together, you're splitting them apart. And so you have a uranium molecule being split into two. And as you have that split, as you have that fission, energy is released, a staggering amount of energy. And that's what nuclear power is today. We aren't using it in bombs. Yes, we still have nuclear weapons, but we're mainly using nuclear power in this way to cause those same fission reactions in order to generate power to turn turbines and produce steam and produce electricity. And so here you see that cloud there with the words cooling tower in it, but that's not pollution like we talked about with petroleum. That's just going to be steam. That's just water vapor that's produced as a consequence of this sort of reaction. So you need to have the cooling water, you need to have the rare earths, you need to have uranium, but um, this is a way to generate energy from those ancient elements without necessarily the waste that you would generate from things like petroleum or coal. You can even try this in your backyard. This is a joke slide, by the way. Don't try this in your backyard. This is actually from an old book called Science Made Stupid. I threw it in there so that you can freeze frame it and maybe laugh a little bit, but no time now. Let's go on. Another radioactive element that we use for nuclear power is plutonium, and this was actually used in Nagasaki. It was a slightly different kind of bomb, and plutonium has a higher yield than uranium. So, plutonium is also used for nuclear power today. The big challenge with nuclear power is that you have radioactive waste generated. Now, it's not released into the atmosphere, it can be removed from the process and stored, but it remains radioactive and it's going to remain radioactive for a prolonged period of time. So, the big challenge with nuclear power has been what to do about the waste storage that is inevitable from nuclear fission, because those barrels can start to degrade over time unless they're constantly maintained. And this has been discussed as well, where there's a couple of different ways to dispose of nuclear waste. Number one is in a human built facility. You can keep it centralized and you can make sure that everything is maintained and being watched, but it has to be continually watched. You have to maintain it and keep an eye on it all the time. And when you're talking about these materials remaining radioactive for literally thousands of years, that is an awful long time to consider maintaining these. So usually the thinking is put it in geological repositories, essentially bury it in a mountain. And so you don't need quite the same level of maintenance. And as long as it's staying in the mountain and the mountain remains secure, then the thinking is that yeah, we can safely store things in this manner. And that's actually been proposed for this mountain in Nevada, Yucca Mountain, which has been proposed for huge chunks of my life as a potential storage for nuclear waste. And in fact, here's a diagram of what's anticipated where you can bring stuff in, you can store it here, but you don't necessarily need to actively maintain it and have constant maintenance because it's at the base of a mountain. It's above the water table, it's below the earth, it's not terribly noticeable. Now, the challenge is Yucca Mountain has been challenged, and I think at the moment it is not a viable idea because even though this is a mountain, you need to build a facility to access it. And based on the radioactivity of the waste, this has to be secure for up to 10,000 years. And that's inconceivable. Humans have maybe made some stone tools like projectile points or Clovis points or something that have lasted 10,000 years, but not a lot beyond that. So, thinking that something this complex would last 10,000 years and that we could assuredly guarantee that in advance is something that simply hasn't been possible. And so, as a consequence, the idea of Yucca Mountain as a nuclear waste storage area has never really taken off. And that's why nuclear waste materials from nuclear fission remains an issue. Now, the eventual goal, if possible, is to move away from fission and move to nuclear fusion. And that's what's happening with all the other energy we're talking about, because we talked once again about getting energy from coal, getting energy from petroleum, getting energy from natural gas, and that is from ancient ecosystems. And those ancient ecosystems got their energy from sunlight, and sunlight comes from nuclear fusion. The sun is essentially a giant nuclear fusion reactor where hydrogen is being fused into helium. And the consequence of that reaction is the release of an enormous amount of energy. And it has been going on for millions of years, billions of years, and it will be going on for quite some time to come. It's actually not a terribly efficient reaction, but because the sun is so big, it's so massive, the reaction continues and will continue to do so. And that's the ultimate source of every calorie you have ever burned, is not just the sun in this case, but nuclear fusion in this case. And so the idea is if humans can recreate that here on Earth, then it becomes a self sustaining operation, and we have an unlimited source of energy because it replenishes itself. And so that has been the drive literally for my whole life. I remember debating this with my geek friends back in high school about how soon nuclear fusion would be possible. And back then we thought maybe within the next 20 years. Well, it was a lot longer than 20 years ago that I was in high school, and it still hasn't happened. So what you're looking at is switching from something like this to something like what the sun is doing. And humans have been working on that. And so this is a fusion reactor. And so there have been a couple of times that we have generated energy this way. But there are key things that need to happen that haven't really happened in a reliable, sustained manner yet. And we seem to be years, if not decades, away from it happening. Number one, the reaction has to produce more energy than it was needed to ignite the reaction. If you're simply recycling the energy that you pumped in, you're always going to lose some because of Newton's laws. However, it has happened briefly in California in December 2022 and again in 2022, where very briefly, for just seconds, if that, there was more energy being produced than was being pumped into it. But it hasn't been sustained. And that's the other thing. The reaction has to be sustainable. And in Korea, they have a facility that has achieved plasma at 100 million degrees Celsius for 48 seconds. And so that was sustainable for 48 seconds. Now, it's not fusion yet because you need to be at least 150 million degrees Celsius in order for fusion to take place. But it does show that they are moving in that direction. But again, not sustainably. All of that is in our future. All of that is in your future. Those are ways to make energy that may happen in your lifetime. But I've been saying that about my own lifetime for my entire lifetime, and so far it hasn't happened yet. Nevertheless, people are trying to achieve this possibility, which would mean essentially unlimited energy for all of humanity. But we aren't quite there yet. Now, in addition to energy sources, which is pretty much all we have been talking about so far, the rock record gives us other things that we use as well. We are in an economy that is based on gold, for example, and so gold is a mineral that's been used for a variety of things. It was what brought the Spanish and other European nations to North America. They were searching for gold, among other things. And native peoples were manufacturing things with gold, so it was here, but it is still relatively rare. There are some abandoned mines from back in the days when gold was being harvested. This is one old gold mine that you can see down in Joshua Tree National Park if you were so inclined. But that is also what led to the population of California and California growing and becoming a state of the union was the discovery of gold. And as people were moving out here and looking for gold and trying to find gold and trying to make their lives with gold, in some cases they succeeded, in many cases they failed, and because they failed, they had no money to go back to their homes. So they stayed here, they raised families here, and as a consequence, that's how California's population initially took off. You can still, if you're so inclined, see some of the remnants of some of these ghost towns in California today. This is the Bodie ghost town, which was a gold mining town and has since been deserted. That's my wife Kim in front of one of the buildings there. It's a nice drive if you want to go. I'd recommend it. You can go see that. But generally speaking, gold has kind of declined in California's history as a source of money, a source of energy. You don't see nearly as many different gold mines as you would have seen during the gold rush. That is absolutely not the case for Nevada. Nevada is still, particularly northern Nevada, is still huge with gold mines. They are all over the place up there. In fact, they're majorly competing with cattle ranching up there as one of the two driving economic forces in northern Nevada. And as you can imagine, the mining there creates enormous pits. Um, and they're running pretty much 24 hours a day, 7 days a week, 365 days a year. The same thing is happening at Molycorp Mine, by the way, where whether it's the rare earths at Molycorp or gold in Nevada, the prices are so high, the profit margin is so great that you need to excavate 24/7 and 365 days a year. They do not get holidays. They do not take Christmas off or Thanksgiving off, nothing like that. Maybe some people do, but there are always people working. They're using some of the largest construction equipment known. Those are, I mean, look at that tiny little guy there. Look at the size of him compared to some of that equipment. And that is running all the time, all the time, all the time. And that huge excavation is paid for because gold is so valuable and is so integral to our economy, our global economy. But you also produce waste. You also generate tailings like this that then sit, and then these can maybe be picked through for more gold at some point, but that's going to be down the road. Other elements that we find that we use for I'm getting back to energy now, but other elements that we use from the rock record would be things like we're using for electric cars, electric vehicles. If you want to get away from petroleum based products, if you want to get away from transportation based on natural gas, increasingly we are moving towards things like electric vehicles, but they also require materials from the rock record, geological resources. In this case, these are largely driven by lithium ion batteries. And you can see here, here's some of the rare earths that are needed, and lithium is needed for grid storage batteries. So if you've ever used a lithium ion battery, you've been using lithium. Lithium is available around the planet, but in varying amounts. Canada has huge resources, huge deposits. Brazil does. China is the number one producer of lithium today. The United States, not as much. We do have some lithium deposits, but not nearly as much as you're seeing in some other parts of the world, like China or Australia or India. Um, and lithium harvesting, depending on where it takes place, can also result in environmental degradation. It takes a lot of effort, and because it's so needed, um, Economics kind of falls by the wayside sometimes. Lithium is frequently excavated under poor working conditions, particularly in some other nations, and can cause damage like this. This is a lithium mine in South America, and you can see the amount of damage that's being done there. And that's not unusual, and the people working there are not necessarily subjected to the best working conditions. Once again, it is a valuable commodity, particularly as the electric vehicle industry takes off, but that doesn't mean it doesn't have its own consequences. Here in Southern California, we've already mentioned the Salton Sea, and here it is again because it has been proposed as a potential source of lithium, so that we are higher on that list of nations producing lithium. This is a report from the end of 2023 that talks about how the Salton Sea region could meet the nation's need for the critical mineral through extraction from geothermal brines. So, here, in addition to the geothermal energy that's available, from the Salton Sea region, you also potentially have a lot of lithium available. However, because of the environmental damage that might be caused depending on how you extract it, it's being challenged environmentally. This is from last month, by the way. So, once again, I'm trying to keep on the cutting edge for you. I'm trying to make sure I'm finding the most recent stuff for you to keep aware of. But it lets you know that people are concerned about this sort of thing because if you don't excavate it correctly, then you could have environmental degradation. You need to make sure that you are excavating things in an environmentally responsible manner. And the challenge there is that that's going to potentially drive the cost up, and then you're competing with other nations that aren't necessarily using those same environmentally protective protocols that we would recommend. So either you damage the environment to be competitive or you find some other way of doing things. And so this is still very much in flux. And finally, I think this is our last mineral. We're going to talk about cobalt, which is another rare earth. And this is used for things like fuel cells and also for nuclear power, but it's also used in laptops and cell phones. It's used in lithium ion batteries. It is a product of it's a geologic product that's used in lithium ion batteries. So, again, if you're using a laptop or a phone or anything with a rechargeable battery, a lithium ion battery, you're almost certainly using cobalt in small amounts, but you're still using it. And the reason I emphasize that is that if we look at the global deposits of cobalt today, you can see that the vast majority, almost half of the global cobalt reserves are in the Congo in Africa. And if you look at how that is being harvested right now, this is what it looks like. It is incredibly poor working conditions. This is some of the nastiest work conditions on the planet. And you and I are a part of this, what these people are being subjected to, because we are all using things like laptops and smartphones and rechargeable batteries. We use them all the time. I do, you do, and these people are paying for that with their bodies. And that includes child labor being used to harvest these rocks so that they can be processed, so that cobalt can be retrieved and then sold and then used in lithium batteries and other things that we use on a daily basis. Cobalt mines, this is a few years back, cobalt mines being linked to child labor. So, once again, and we'll talk about this in a future lecture, but what we are doing today to get off of one energy source and onto another, it has consequences. It has consequences for the environment and it has consequences for people. Those consequences can be addressed and dealt with more money, but that's going to either drive up the prices of your laptops or your phones, or it's going to cut into the profits of some of the corporations responsible for producing the things that we use. And so far, that hasn't been a driving force. So, next time you're using your laptop or your phone or a rechargeable battery, be aware of what's going on with the power that you're using. I'm not trying to give you a guilt complex, because if I'm giving you one, I'd better take a hefty dose of that guilt myself, because I'm using a laptop right now and will be using a phone as soon as I finish this lecture. So I'm as guilty as anybody else. But we need to all be aware of the consequences of the way we're living our lives. And with that, I believe that is the last slide for this lecture. Once again, if you have any questions, please feel free to reach out. Happy to speak with you. Otherwise, have a good evening. Take care of yourselves, and we'll see you later in the week.